All right. Uh, okay. Thank you to Prof. Winkler for the excellent talk, and thank you to Zhao Ying for hosting this. So next talk is from Ashraf Abdul, who is a PhD candidate working with Prof. Brian Lane and Prof. Mohan Kankahali. So his doctoral research helps improving the human interpretability of explanation for artificial intelligence based decision-making system through theory-driven integration of human factors. So Ashraf, are you there?
Yep, I'm here.
Yeah, okay. I'll make you co-host so you can share the screen. Yeah. Right.
Okay, so let's get started. Hi everyone, I'm Ashraf. I'm a PhD student at the School of Computing, and today I will talk about how we can measure and moderate cognitive load in machine learning model explanations. This work was done in collaboration with Dr. Christian Wonderweth and my PhD advisors, Professor Mohan Kankanhali and Professor Brian Lim. I'm also a part of the NUS Ubicom lab, and our lab develops intelligible AI-driven applications for healthcare and smart cities. Artificial intelligence, or AI, now touches many aspects of our lives, and it helps us make many decisions. And AI can even help you predict the price of a house. So say you are looking to rent this house. How much do you think you would pay for rent? Well, you could ask an AI about it, and let's say,
Sorry, Ashraf. Could you please volume up? Your voice is a little bit low. Yeah.
so you could ask the AI about it, and let's say the AI tells you the house costs $7,000. So that's quite cheap for such a large house. How did how do you think the AI calculated this price? Well, it could have considered several factors, such as how many rooms are there in the house, how far the house is from the business district, whether there are good schools in the vicinity, and so on. But how do you think it reasoned about these prices? Well, we are lucky because we have an explainable AI, and we can simply ask it, why do you think the house costs $7,000? And let's say the AI provides a visual explanation that looks like this. So it tells you that when the number of rooms increases by one, the price increases by $3,000. And when the distance from the business district increases by one, the price decreases by about $1,200. And it also tells you that as the student teacher ratio increases, the price of a house decreases. By the way, this visualization is called a lollipop chart visualization because, well, the bars look like lollipops, and the height of each lollipop is proportional to how influential that factor is. Um, these lollipop chart explanations are generated from a linear model. And what that means is that uh, the price either increases or decreases linearly with the factors. Now, if we were to use them to predict the price of a house, let's say this house had 8 rooms, was 3 kilometers away from the business district, and had about 15 students to a teacher, then the AI explanation says that the price should be around $10,000. But this is way off from the AI prediction, which is about 7,000. So there's about roughly 4,000 difference in the price. And why do you think this happens? This is because, well, can the price of a house really depend on only three factors? Probably not, right? We know there should be many more factors involved. And the second point is that rarely does two things in the real world increase constantly or decrease constantly um, show a linear relationship. So in fact, the previous example, the visual explanation was generated from something called as a sparse linear model. And sparse means a few. In this case, it was only showing three factors. So let's add some more factors to this explanation and see if that makes a difference. And we've got a lot more factors now. And if we try to redo our calculation this time, well, the price is somewhat different. It's about 9,700, but you see it's still way off from the AI prediction. And this is because the assumption of linearity is just too strong. In the real world, we expect price to not change at a constant rate, but show many variations. So now we could ask the AI for a more expressive explanation. And then the AI provides us with a detailed explanation in the form of line charts. And these help to capture the complex nonlinear relationships of the factors with the price. And by the way, this visualization is generated from a generalized additive model, or GAM, that is also read as GAM. So now let's try and calculate the price of a house. Well, unlike the linear model, what is immediately obvious is that the price doesn't always increase with the number of rooms. It's relatively flat at the beginning, and then there's a sudden steep rise. So when the number of rooms is 8, the contribution of the price is about $4,300. Similarly, we could look up the contribution of all the other factors. And if we did this for each factor that was explained, and then compute the price by adding all of those contributions up, then we'll notice that this time the explanation is actually pretty close to the prediction. But we had to examine many complex nonlinear relationships to get there. So on one hand, we have sparse linear models that are pretty easy to read, but they're not so accurate. And on the other hand, we have generalized additive models that are difficult to read, but they are also more accurate. Slide seems to be stuck. Yeah. So can we have explanations that are both accurate and easy to read? And this is where we present COGAM, or cognitive GAM, that helps generate explanations that are both easy to read and accurate. But before we can understand how to generate these explanations, we want to understand what makes a graph easy or difficult to read. And to answer that, we look at experimental studies from cognitive science and psychology on what makes a line graph difficult to comprehend. And we find that there are many factors that affect their comprehension. In this study, we only focus on the most salient one, which is the trend reversals. A trend reversal occurs when the direction of the line changes and the line starts moving in the opposite direction. And what you will notice is that this graph has many trend reversals. So what previous research tells us is that cognitive load of reading the graph increases as the number of trend reversals increase. And as you can see, the graph on the right does seem a little easier to read. This is because users visually chunk the graphs into approximately linear segments while they are trying to understand the graph. And since the graph on the left has 7 approximately linear segments, it takes much longer to read than the graph on the right. So to reduce cognitive load, we need to reduce the number of chunks in a graph. And the first way that we just saw of doing that was by reducing the nonlinearity. What we could also do was just make the line completely straight, right? And in which case there's just one linear line chunk that the user needs to see. And this is much more faster to read. Now the salient information in a line is the slope. So we could also represent a line as a lollipop bar such that the influence value was same as the slope of the line, and a lollipop bar is much more faster to read. Finally, we could just zero out the graph. That is, we do not show this graph to the user. And in that case, since the user sees nothing, it doesn't impose any cognitive load. So we're going to consider these strategies to reduce the cognitive load of an explanation. But we'll start with how we can train a GAM. Training a GAM involves learning a line that is indicated by the function f, which best predicts the data. So in this case, you want to learn the relationship between the number of rooms on the x-axis and the price on the y-axis. And this function can be learned by minimizing this objective. Let me try and break this down for you. It consists of two parts. The one on the left measures the error between the prediction line and the ground truth. And the one on the right controls for how wiggly the line is. The weight lambda trades off between the prediction error and a smoother line. So if the value of lambda is lower, then the line is more wigglier. And for a higher lambda, the line is more smoother. And in this case, we specified the GAM to learn a nonlinear shape function. But you could also specify to learn a linear shape function. This is useful when you know that the true relationship in the data is linear. And this objective function applies to one factor. As you can see, we've learned the relationship between the number of rooms and the price. If there is more than one factor, then we learn a different shape function for each factor. So recall now that our approach to reducing cognitive load was either to make a factor less nonlinear, make it fully linear, or zero it out. So with this background, let's see how we can train COGAMs. We'll start with an example that has three factors. On the left, you see the scatter plot of the raw data, and on the right, you see a table with some scores. So the mutual information score of a factor tells us how predictive a factor is towards the price. So a lower score implies that the factor is less predictive and hence is a candidate for removal. The R-squared score of the straight line fit tells us how linear the relationship between the factor and the price is. So a higher score implies a more linear relationship, and we might want to model that factor linearly. So now let's start first with zero zeroed factors and zero linear factors. In this case, all the factors are fit non-linearly. So we train the COGAM based on the objective function that I just described. And once we've trained the model, we record the number of visual chunks and the resulting accuracy on the test set. Now let's try and train this by zeroing one factor and making the other factor linear. First, to decide which factor should be zero, we choose the one with the lowest mutual information score. In this case, it is the distance to the business district. Next, to decide which factor should be made linear, we select the one with the highest R-squared score, which is the number of rooms. And the only remaining factor is modeled non-linearly. And same as before, we calculate the number of visual chunks and the resulting accuracy. So if I were to repeat this process systematically, each time enumerating over the different combinations of zeroed and linear factors, then we'll get a table where each row is a different model and each model has a different number of visual chunks and accuracy. And now what I'm going to do is I'm going to plot these models using a scatter plot such that the accuracy is on the x-axis and the number of visual chunks is on the y-axis. So each blue dot here is a row from the table that indicates a different COGAM. What you will notice is that as we move towards the bottom right in this graph, we find models that have both high accuracy and low visual chunks. And if you were to find the sparse linear model, it's all the way towards the bottom left. As expected, it has low accuracy, but also low cognitive load. Interestingly, in this highlighted region, there are many COGAMs with higher accuracy than the sparse linear model, but with lower cognitive load. GAM is again all the way up to the top, and we expect this because it has very high accuracy, but also very high cognitive load. The more interesting result really is this highlighted region where we find that there are many COGAMs that have a higher accuracy with GAM, but they impose much lower cognitive load. So COGAM is able to find many solutions that have both high accuracy and low cognitive load. But how does theoretical cognitive load in terms of visual chunks translate to empirical cognitive load that a user experiences? And how does AI accuracy translate to the human plus AI accuracy after the user sees the AI explanation? So to answer these questions, we calibrate the empirical cognitive load in terms of the reading time of an explanation. And to understand the human plus AI accuracy, we examine the user's mental model and we also check performance on some human simulatability tasks. Let's start with the calibration of the cognitive load. So to calibrate it, we do a between subjects experiment where each user sees a different model. So some examples of this different models are, this is one of it, and there's another model which has a different number of visual chunks. So each user sees a different model and each of them have different number of visual chunks. And then we ask the users to study the explanations for as long as it is required. And we tell them that they will have to answer questions based on these explanations. The time that they spend reading this explanation is recorded. And finally, we ask them many different questions to serve as controls that check a user's understanding. More details of these questions are in the paper. Now, if you look at the results, on the left is the plot that you already saw, which was in terms of the theoretical visual chunks. And on the right is our new plot where the y-axis is in terms of the log of the reading time. The first thing you'll notice is that, wow, they look similar. So this does confirm empirically that there are many COGAMs that are faster to read while having a better accuracy than GAM. So next what we do is we select one of the many COGAMs, the dot here in green, and we choose it such that it has a similar reading time as a sparse linear model, but accuracy comparable to GAM. And then perform a between subjects experiment to assess the mental models of the users. So users see one of the three different explanation visualizations, and just as before, they are allowed to carefully study them. And once they are ready, the visualization is hidden and they are asked to retrieve from memory details of some randomly chosen factors. So in their condition, if there was a factor that was visualized as a nonlinear line graph, then the users are asked to draw the line which describes the relationship to price. And if there was a randomly chosen factor that was a lollipop, then users are asked to specify the influence value of the factor output relationships. Finally, the user mental model is reconstructed from the factor outcome relationships that the user has recalled from memory. And the explainer model is simply one of the three different models based on the condition. And what we really want to know is how similar is the user's mental model of the explanation to the explainer. So to calculate their similarity, we use the models to make predictions on the test data set, and then we calculate the R-squared score. So a higher score implies that the user's model of the explainer is very similar to the explanation that they just saw. And if I do the same plot that I've been doing so far, this time with the recall reconstruction score on the x-axis, then where a higher score indicates that the user had a more accurate mental model, you will notice that COGAM is towards the bottom right? So this indicates not only is COGAM faster to read, but it also helped the user create a more accurate mental model. And what this tells us is that simplifying explanations to reduce cognitive load does not necessarily reduce the knowledge gained by the user. As you can see, GAM, despite having high explanation accuracy, had poor user mental models. So COGAM is able to find explanations that balance cognitive load and accuracy. The implication of this is that explanations can now be tuned based on the cognitive load and accuracy requirements of the domain. So what do I mean by that? Let's say we have a consumer application for rental price prediction. We want to improve the usability of the explanation by reducing the cognitive load. So we'd want to pick some model that's towards the bottom left of the plot. But if this was the healthcare domain, we want to tune for increased accuracy where it is worth the additional cognitive load. Finally, COGAM is an example, the research methodology is an example of theory-driven integration of human factors in XAI. What do I mean by that? We all know that explanations help users understand models, but explanations themselves impose some cognitive load of interpretation. Now, researchers have used the principle of sparsity as a guideline that showing fewer features is more usable. But how few exactly? So to answer that question, we ground ourselves in graph comprehension theories. We use that grounding to create mathematical models that help us simulate and understand the trade-offs between cognitive load and accuracy. And finally, we test the practical usability of the improvements through empirical verification with novel measures that assess our new proposed approach. So if you've been with me so far, thank you for your attention. Please do check our paper for more details. You could also visit our lab website for other human-centric XAI works by using the QR code at the bottom left. And I'm happy to take questions now.
Okay, thank you, Ashraf. So we have time for two questions. So here we have a question from Karim. That is, how is it possible for the COGAM or the models in between to be more accurate than GAM? Doesn't that mean that GAM was poorly trained?
No, I mean, so in our experiments, what we do is we always select the best model based on the performance on the test set, right? And do I have appendix slides? Yeah. So in fact, there are other GAM training approaches which can have better accuracy. An example of that is GAMCell here. The GAM here was trained using penalized iterative reweighted least squares approach. Yeah, but there are other GAM formulations that can probably have higher accuracy. The reduction in cognitive load is really just coming from the fact that the reduced nonlinearity contributes fewer visual chunks. That's point one. Point two is that, which is more subtler, is that it's related inherently to the nature of the data set, right? So a data set might have more or less combinations of nonlinear factors, and that really changes the trends. So in our simulation experiments, for example, you will see the plots on the left for Boston housing and Ames housing data sets. You will see that COGAM can actually have both high accuracy and low cognitive load. But for other data sets like wine quality and concrete strength, that's not possible. So you have to trade off between accuracy or cognitive load.
Okay. So the last question is, why the number of rooms in house has non-integer value? There are so many chunks in number of rooms versus partial price figure. Is that a sign that the game is overfitted?
That's an excellent question. Yes, so generally GAMs are indeed prone to overfitting. It depends on the way you model it. So if you do it with cubic splines, which is what is done here, you see a lot of these peaks in the nonlinearity, which contributes to the chunks. So there is a notion that they can tend to overfit. There are newer GAM training approaches that looked at using uh, decision trees with bagging to train the GAMs, where your shape functions are still nonlinear, but they are like they look like step functions. So yes, the short answer is GAMs are known to overfit in general.
Okay, okay. Thank you, Ashraf, for coming for this talk. Okay, so if you're interested in this work, please contact Ashraf directly. And okay, now let me hand over to Vijay.
Thank you, Ashraf, for the wonderful talk. So for the next talk, we have Marcia Ray, the final year PhD student at Center for Quantum Technologies. And he will be talking about strategies for quantum races. So let's go.